All right, so we just watched the Party-Sabetti video explaining the central limit theorem, and they talked about things, and now we'll just kind of give a brief overview about what we just saw, okay? So first, we have some terminology that we already know, that this mu is a population mean, or a parameter. And X bar is the symbol we use for a sample mean. And what is the word we call for a sample mean? A statistic. I'll zoom in a little bit so that it's a little bit neater. Okay, a sampling distribution of means is a chart of all of the X bars from a distribution of all of the X bars from so it's a distribution of all of the X bars from taken samples of the same size. Doesn't matter what size it is, the smaller or larger. Now, we are going to do our own little examination of the central limit theorem here using dice. Okay, so everybody gets a dice. And we don't have to use the dice for our number one, which is to draw a sketch of the population and its distribution. And, you know, might as well do it. Cool. I'd like everybody to roll their dice 10 times. Okay, hold on. And keep a tally of how many 1s, 2s, 3s, 4s, 5s, 6s you came up with. Okay? So I'm going to do the same thing as well. We're going to then kind of graph things over here. So go ahead. Roll your dice 10 times and keep a tally of how many 1s, 2s, 3s, 4s, 5s, 6s. Okay, so I got 1, 1, 2, 2s, 3s, 1, 4, 3, 5s, 1, 6. Put up in with your hands or hand, how many 1s you got? 1 plus. You got 0, 2, 2, 1, 1, 2, 2, 1, 2, 2, 1, 1, and 1. So the entire class had a total of 19 1s. Okay, then let's do the same thing for 2s. Yes, 19 including mine. So 6, 2, 2, 2. Is that 2 or 3? 3. German. 3, 1, 2. I said, what are you, German? That's how they count. 1, 2, 3.
I take a pen.
It's sign language? Yeah. Oh. 31. Wow. How many 3s do we all have? 2, 3, 3, 1, 1, 1, 3, 2, 1, 2. How many is that? 1? 2. 21 threes. 24s. 1, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. How many 5s? 1, 2, 3, 4, 6, 7, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And how many 6s? 1, 2, 3, 4, 5, 6, 10, 12, 13, 14, 15, 17, 19, 22, 27. Okay, now, obviously, if we all rolled 50 times, what do we think we would see? They'd be pretty close to the same in terms of the amounts, right? So, but right now we could say, okay, 19, 31, 21, 16, 24, 27, something like this, right? And this is our graph that we're doing actually right here. But what you can say is for 1s, 2s, 3s, 4, 5, 6, you can assume that they would be uniform, right? Straight across. So go ahead and just kind of do something that's straight across. Well, I mean, we understand that with smaller sample size, there's variability. And this is why people do go to Vegas, even though they know that their expected value of playing every game is negative. Because there's variability with smaller sample sizes. So just don't live in Vegas and play all the time. But show up to Vegas and play for an hour, small sample size, you might end up winning more than you lose. Does that make sense? Okay.
You seem to encourage gambling a lot in this class.
I do not. I just say why people do it. And a lot of probability, is shown in games that are gambling games.
What about the day where you taught us?
I taught you a game. That is a very famous game when reference to probability. Okay? Now, straight across. Each point in the area of the graph represents, a data point, but don't worry about that. Just don't worry about this. Okay, describe the population distribution. We would call this uniform. Okay, straight across. Now, what we are going to do, and I don't want us to do what they do, is we're going to toss our dice 10 times again. But we are going to record the average of our 10 throws. Okay? And we're going to draw a sketch of the average of our 10 throws. So let me show you what that means. I'm going to do it first, and then you guys are going to do it as well. I'm pretty sure most of you will understand it, but I want good data, so I'm going to do it for all of us. Okay? So I roll. I got a 1. I'm going to actually write it down. Then I got a 3. It's going to help if you actually write it down. 1. Then I got a 3. Roll again. I got another 3. I got a 6. I got a 5. 3. 4. 4. Whose number is that for? Whose number is that for? Yeah. Okay. 3.
We're all done. It's over.
Okay. Now, so that is a sample. Now, what I'm going to do is create a sample mean an X bar. How do you find the average of this? Do I need to go to stat edit and type it in and do, yeah, I can just add all of these up and divide by 10. Okay, now we would do this in parentheses before we divide by 10 in our calculator. So let's just do that. I'm going to add all the numbers. 1 plus 3 plus 3 plus 6 plus 5 plus 3 plus 4 plus 4 plus 4 plus 3 divided by 10. And I get 3.6. You guys do the same thing, okay? Go. You got it, Miss Harden? Write down your number for each throw, and then let's find the average of the 10 throws. You got it? You same? Cool. Okay, so I got 3.6. I'm going to just put mine right here between 3 and 4. Okay? Miss Big Pen, did you get yours? What did you get? Yep. 2.8. So Miss Big Pen got 2.8. And Miss Harris, what did you get? I'm going to go ahead and split these. I'm just going to, well, how many total data points? Yeah, I'm going to split these into halves, actually. I think that's valuable. So I'm at 3.6. Miss Big Pen, 2.8. Okay. Miss Harris, 3.9. So you're going to go on top of mine. 2.8 as well. Mr. Polkowski, 3.6. Ms. Harton, 3.6, okay. 3.3. 3.1. Mr. Dantua, 3.6, popular number. Really? Unbelievable. 3.6. 2.8. 3.2. 3.1, 3.9, okay? Now,
I think one of those was not 3.6, maybe 2.
Yeah, right. Now, what would we expect our average roll to be? Would it be 3? What would our expected roll be, right? Well, we could actually calculate this. We know expected value, right? What's the average of getting a 1? What's our probability of getting a 1? 1/6, okay. What's our probability of getting a 2? What's the probability of getting a 3? Okay, let's do this math in our calculator really quick. What would be our expected roll each time? Yes!
You just get it by adding up 1, 2, 3, 4, 5, 6, and then divide it by 6.
Yeah, sure.
I didn't want to do that.
So we expect to get there. Well, 3.6 is good. But what you can see here, and probably if we did a larger sample size, we'd see actually a smaller sample size. We'd probably see like a 4.1 or 2. And then maybe a 4.6. We had a couple there, but we see, it's not obvious, but you can see that it's not uniform. You obviously see that this is not uniform, right? Why? Because we took an average of ours. Whenever we took an average, well, the 1s and the 6s kind of cancel each other out. The 2s and the 5s cancel each other out. You know, the 3s and the 4s kind of cancel each other out. And we ended up with, you know, sample means of 3.5. And all of a sudden our distribution, which was uniform, became normal. Centered around the mean, 3.5, which is also the mean for this, if we actually did the math, okay? Each point in the area, so, you know, we had points here. Each of these points represented sample means. This is the distribution of X bar. Okay? How does the center, shape, and spread of the sampling distribution with n equals 10 compare with the population? It's completely different. But the center ends up being the same. The shape is different. The shape is normal. And the spread has shrunk as well. We are spread all the way out from 1s to 6s, evenly amounts. The standard deviation would have definitely been spread out. But here, we are all kind of focused around the middle, so the spread has shrunk. This is the essential limit theorem in action. Okay? Now, here's the essential limit theorem stated with the definition. For a small sample, the sampling distribution shape is similar to the shape of the population's distribution. But as the sample size of your samples increases, so if we took a sample size of 20 instead of 10, if we took a sample size of 10 instead of 3, the more normal we are going to see our distribution get. Population distribution, POP-DIST. The mean of the sampling distribution, however, is going to be the same as the mean of the population. But as your sample size increases, if we threw our die 20 times, if we threw our die 30 times, if we threw our die 50 times, we would find that the standard deviation of the sample distribution would keep getting smaller and smaller, because the peak of our curve would get higher and higher, because we would be all kind of centered around the mean. Sampling distribution shrinks or gets smaller. And how much smaller does it get? Well, it gets this much smaller. If we take the sample standard deviation and divide it by the square root of our sample size, now what we will find is when we do problems, we are going to make a lot of assumptions. We're pretty much going to be given one sample size, and we're going to say, well, we're going to be given one sample. And we're going to say, well, let's just assume that sample represents all of these samples that we are going to be using. So we'd use like the sample standard deviation and n for all of that. Tough to ask questions about the central limit theorem. All right, quick example. Researchers want to estimate the average number of pets in the American household. Describe the sampling distribution of sample means of sample size 200. They assume past data is still accurate, with an average of 1.8 pets and a sample standard deviation of 2.4. Well, we would, we could draw a normal curve to kind of see that. And this would be the distribution of x bar. And we know that the mean would still be the same. So that means this would be 1.8. However, the standard deviation of 2.4, we would have to adjust, and we would say the standard deviation of my sampling distribution would be that 2.4 divided by the square root of 200. And it would shrink that sampling distribution. Okay, so this would be the mean. This is mu, and it's also, the mean of all of my x bars. And let's do the calculation, this in our calculator. And this is us describing sampling distributions. Whenever I asked you last unit to describe the sampling distribution, you just tell me what the mean and the standard deviation is, and that would be it. Again, 0.1697. Dot, dot, dot. Okay, and this is a standard deviation that you can add to 1.8. So if this is 1.8, you can add 1.8 to that. And we could go one standard deviation away. We can go 2 standard deviations away by adding that again. And this is how you could, draw your normal curve with some specific data. Okay, and you could do the same thing if you subtracted. Okay, again, that's when you add the actual standard deviation. We are still going to be using z values. We're going to switch it over to another type of value, a t value. And that's when you use 0, and this would be a z value of 0, 1, 2, -1, -2. Okay? We go with that. So that's essential limit theorem, and that's actually going to lead us to the next part of this lesson, part B, which will be confidence intervals, not for proportions. Okay? So it's very important that, last unit or the last 2 units, we've been talking about proportions. So all of our proportions was percentages. And we'd have a confidence interval of 62% to 68%, and we'd say we are 98% confident that the actual parameter is between 62% and 68%. Well, now in this one, we are going to be talking about specific sample data. So heights of things, lengths of things, weights, whatever we can take measurements of, and their units are not going to be percentages anymore. Okay, so that's going to be one key difference between the previous units and this unit, is we're not doing proportions anymore, which means our standard deviation calculations are no longer going to be the square root of p times 1 minus p over n. We're actually going to use our calculator to do our standard deviation calculations, or we are going to just be told what our standard deviation is. But we're going to keep the concept from this, which is we're going to be taking sample means, and since we are taking sample means, we're going to need to use this formula, okay? And things are going to change a little bit because we're going to talk about specific situation when our sample sizes are not very large. And when our sample sizes are not very large, instead of using a z, which we're used to using, you're switching it up with a t. And to explain that a little bit better, I give you Miss Participating. So, We're back after a party video, and we are talking about producing confidence intervals. Now, the confidence intervals are not going to be of proportions. They're going to be of data. We are going to use this formula, which we are familiar with. It's just adjusted a little bit. We are used to the formula of a P plus or minus a Z times P times 1 minus P all over N. Well, that's essentially the same exact thing. All we're doing is we're taking something and adding and subtracting a margin of error, right? A margin of error comes from a standard deviation distance times a standard deviation. This was our standard deviation for a proportion. Well, now we are going to take data and sample data. So like an average height, an average pH level, an average density level, an average weight of something. This would be our data. And then instead of adding and subtracting a Z value, it will depend on our sample size, what our T value is. And then we are going to have that concept of a sampling distribution, and we will have a standard deviation of a sample mean divided by the square root of n to get our sampling, our standard deviation of our sampling distribution. Central limit theorem. We are going to be typically just using our calculator, and we are going to use stat test T interval. Okay, everybody in your calculator, let's familiarize ourselves with stat test T interval. We are used to Z intervals for confidence intervals of proportions. We actually had Z tests for proportions here, 2 proportions Z tests, that was from last unit. And now we are going to do stat test 8 for a T interval. And notice when you select it, we have 2 things that pop up, data and stats. And it depends on the situation, whether we are going to produce our interval, our confidence interval, from data that we are going to enter into stat edit, or from information that we're given in a problem. Okay, so there's 2 situations that we have to just be aware of, and we are going to make sure we select the correct one when we are calculating the interval. Okay? Now, the things that we learned 2 units ago about confidence intervals still apply. So you answered this question 2 units ago, and you should be able to answer it today. A larger confidence level makes the margin of error what? Wider is correct, Mr. Galt. Excellent. Would a 90% or a 98% confidence interval be wider than the other? Discuss amongst your neighbors, okay? Make sure we understand. And if you don't understand, ask your neighbor why you chose that answer. Okay, Ms. Curdy and Ms. Harris, I want you to try to get the right answer. And Ms. Thigpen, you 3 over there.
Certainly, I am certainly agreeable.
All right. So, Mr. Smith, can I ask you which one would be wider, and can you give me a correct answer? Which one's wider, the 90 or the 98%? Yes, the 98%. Okay. To be more confident, we just need to stretch things out a little bit. Okay, and the more we stretch it out, if I went from 0 to 100% is what I'm used to doing with proportions, but now we say a weight of between 0 and 1,000 pounds, I am 100 or I'm 99% confident that the weight of the average of you guys is between 0 and 1,000 pounds.
I mean.
Okay, right? Doesn't that make sense?
That is pretty accurate.
Right, probably be 100% confidence, right? Then you can never be 100% confident. All right, now we talk about sample sizes. Now, again, let's talk about the average weight of you guys. Okay? The larger the sample size, would that mean my confidence interval would have to get wider for me to be confident, or the same amount of confident, or does it naturally have to get smaller? I kind of gave you the answer by saying naturally. But yes, smaller, and Mr. Smith was correct. Smaller, it would get narrower with a larger sample size. So we could keep the same level of confidence, but shrink our confidence interval because we have a larger sample size. We talked about this so much 2 units ago. So which one would be wider? Answer this question, discuss it with your neighbors, and let's make sure we're on the same page with that one. All right, Mr. Galt, sit up and answer the question. 100 would be wider, okay? We have a smaller sample size, which means the smaller sample size would need a wider confidence interval to have the same level of confidence. Okay, the rest are going to be just using stat test 8, our new friend, to answer the following questions to produce the confidence intervals. So here we go. The director of our hospital wishes to estimate the mean number of people who are admitted to the emergency room during a 24-hour period. Notice how the question changes from 2 units ago. It's an amount of people. It's not a proportion anymore, okay? The director randomly selects 64 different 24-hour periods and determines the number of admissions for each, okay? So all of a sudden we see that we have a sample size. Have we talked about the degrees of freedom yet? So we Party talked about the degrees of freedom, but it's very important because this will determine the t-value used. The degrees of freedom is determined by the sample size minus 1. Okay, it's very important. Depending on what stat test 8 will ask us, and let's look in stat test 8. Ms. Harton, let's look in stat test 8. And if we go into stats, what do they ask for? Do they ask for the degrees of freedom, or do they just ask for n? N. So it's important to know that you don't need to type in the degrees of freedom, but we need to have a concept in our brain. So the degrees of freedom will always be n minus 1. However, your calculator will do that calculation for you. It will subtract 1 to pick the correct t-value for you. You do not have to find t-values. It is not something we have to do in this course. The calculator will do it for you. Okay? Okay, so here we go. 64 is n. She calculates an average of 19.8 admissions and a standard deviation of 6. So we say that her sample mean for her sampling distribution is 19.8, and her standard deviation, and I'm using S instead of sigma because it's a sample standard deviation, is 6. Construct a 95% confidence interval for the mean number of admissions during a 24-hour period. Okay, let's go to our friend stat test 8. Go. Are we in stat test 8? Now we're up at the top, and do we have a list of data that we should go into stat edit to type in, or do we just have some information, some statistical information? And yes, we just have some info. So we're going to go to stats, and we're going to type in what we are given, that the mean for this sample of hospital stays was 19.8. The sample standard deviation was 6. And they don't ask for DF, they ask for just the sample size. This person took 64. Now, I'll tell you right now, 64, is that a small sample size or a large sample size?
Not large, very large.
Large, if we're taking, samples of 64 every single time, and this is what we are assuming, we are taking samples of 64 each time. That's large. What we will find is that our confidence interval that we are going to produce will be very similar, if not the same as a confidence interval with a z-value that we use if we do the calculation. But that's all we have to do, 95% confidence interval. We press calculate, and poof. Notice our answer, not a proportion. It's in terms of amount of people who are admitted to the emergency room during a 24-hour period. And there's our answer. We would say we are 95% confidence that the true what? Yes, the true mean amount of people who are admitted to an emergency room during a 24-hour period. True mean amount of ER visits, ER admissions, is between 18.3 and 21.3. We'll just round there. You may go as well if you need to. Number 2. Suppose that the forearm lengths for a randomly selected sample of 9 men are, now, we'll talk about this question a little bit more. 25.5, 24, 26.5, 25, blah, blah, blah. Sketch the graph of the data to make sure it's approximately normal since the sample size is so small. I don't want to do this because what we are going to do is we're going to assume that we took this many samples of 9 men. We're changing up the way we think about the problem so that it fits. And this is what we have to do some of the time. This is not, don't think of this as 9 individual men, even though that's what we're doing. Instead, think of this as a mean of 9 men sample. And this is another mean, and this is another mean. And all of a sudden, this would be a sampling distribution of means. Does that make sense? So you can go ahead and just assume. You don't have to worry about it. We just assume that it is going to be normal. And we're going to assume this is an X bar, and this is an X bar, and this is an X bar, and this is an X bar. They're all X bars. So this is, central limit theorem. We guarantee that by the central limit theorem, we will be approximately normal. Let's construct and interpret a 99% confidence interval. Well, we could do this using stat test 8 and stats, but we'd have to calculate the stats ourselves.
Or you could just use data.
Or we could go over to the data section, which means they're going to take the list from L1. Let's go ahead and go into L1 and enter in our data. Yeah, stat test 8, but before that, we're going to go and enter in the data into stat edit. Did you do it already?
Yes, sir.
Not all of us. What is the frequency? Just 1. So frequency is like, how many of these do we have each time? Okay, so we have 9 X bars is what we're thinking. Okay, we have 9 X bars each created with 9 people. Stat test 8, we don't go to stats, we go to data. We'll use L1. Frequency just stays as 1. We want a 99% confidence interval. Boom. And we can say we are 99% confidence that the average forearm length for a male is between 23.799 centimeters and 27.201.
Oh, Lord. Sorry.
Going out of nowhere.
Now we know what mistake Ben listens to.
Ow, my stuff.
Mhm.
They found out 2 days ago that I friend's a SoundCloud rapper.
Suppose an article claimed that the mean form. Suppose an article claimed that the mean forearm length for men is 27 centimeters. Is this claim reasonable or not? It's in our confidence interval. It's reasonable.
Extremely reasonable. It's like, it's so good.
We
I like it. So good.
And that's it. Good job. Here's your homework.
get it.